Okay, so let's look at our first problem. Our first problem here is we have a tank. And this tank is completely insulated. So here's my insulation on the outside of the tank. So that means, what does that mean? That means that there's no heat transfer being added to the tank. And we're going to say this tank is originally a vacuum, V-A-C-U-U-M, and the volume of this tank is 10 liters. Okay. Now here's what's going to happen. This tank is going to develop a hole in the side of it. Maybe rust, something happens. And what's going to happen here is an air from the outside is going to start rushing into the tank. So the surroundings are going to start rushing into the tank. And the surroundings are 1 bar, and they're 25 degrees Celsius. And this is going to happen. This is going to rush in until finally, what's going to happen is that this tank is going to be at 1 bar. So it started as a vacuum, and we're going to have air rushing into the tank until we get it to be 1 bar. Makes sense. This could happen. A vacuum tank that has a little pinhole. Surroundings rush in until it reaches its equalizes the pressure. And we want to find out 2 things. Number 1, what is the final temperature? What is T final in the tank? And 2, how much air leaks in? How much air leaks in? Now you may look at that and say, well, it's obvious, Dr. Winkland, the final temperature of the tank is 25 degrees Celsius because the air is rushing in. But remember, this air is rushing in. It's coming through a pinhole. It's coming in quickly. The temperature is actually going to be hotter. It's going to be a higher temperature than when it was out there at the beginning. It's going to be a much higher temperature. And it's the same thing as the opposite. You dealt with the opposite. You've dealt with a container maybe of air, compressed air, or maybe just even a spray paint can that you sprayed. That's a transient system because the mass is changing with time as it's leaving. It's not steady state. That the mass in that spray paint can is going to change with time. And as you sprayed it, if you hold it down, you're going to notice that can is getting colder. Okay, the can is getting colder because of the mass leaving the system. Same thing's happening here. Here's a transient system because the mass of our control volume, if I were to make our control volume, look at this green line, that mass is not going to remain the same over time like it does in all our other problems. This is now changing with time, and so we're going to have to do something to analyze it. Okay, so what do we have here? Well, let's look at our assumptions. We're going to assume some things. And the first thing we're going to say is the heat transfer is equal to 0. Okay? It's insulated. Okay? We're also going to look here and say the work is equal to 0. There's no boundary work. There is no shaft work. There's no electrical work that's happening here. We've already said that kinetic energy and potential energy is equal to 0 in the kind of the starting things off. We're going to go, this tank is not moving. There's not going to be any appreciable change in the kinetic energy or the potential energy of this system, And we're going to say this is going to be constant specific heat. Constant specific heat. And we're going to say that we're going to say K value is equal to 1.4. So we didn't give you C sub P or C sub V, we gave you K. Okay, what do we do here? Well, the first thing we do is we look at our mass continuity equation. We say the change in mass of the control volume with respect to time is equal to the summation of the m dot in minus the summation of the m dot exiting. Okay, what I'm going to do here is I'm actually going to do a little bit out of order from what I told you earlier. I said we're going to integrate these equations and then we're going to simplify. I'm going to simplify this one right now. There's no mass exiting. It's going to go away. Don't have to worry about that. And now we're going to integrate that from 0 to t dt and from 0 to t dt. And what we're going to get is, we're going to get that these dt's cancel. And we're going to get the mass of the control volume at time t minus the mass of the control volume at time 0 is going to be equal to the mass n, or I can say that mass 2 minus mass 1 is equal to mass n. That makes a lot of sense. The mass of state 2 minus the mass of state 1, mass at time 2 minus the mass at time 1 is equal to the mass coming in. Okay? And this problem is unique in that the mass at time 1 or the mass at time 0 is 0. So here it's pretty easy that mass 2 is equal to whatever mass comes in. Done. We took that big long equation and make it into a very simple small equation. All right, now let's look at our energy equation here. We have the change in internal energy of the control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates in times my enthalpy in minus the summation of my mass flow rates exiting times my enthalpy exiting. We're getting rid of our kinetic and potential energy terms. We already know some things. We know that it's adiabatic. We know that there is no work. And we know that there's no mass exiting. So again, we're simplifying here before we're going after it, and we're going to then integrate this from 0 to t dt. And from 0 to t dt. This cancels here, and we're going to get the internal energy of the control volume at time t minus the internal energy of the control volume at time 0 is going to be equal to the mass in times my enthalpy in. Okay. Or I can call this internal energy 2 minus internal energy 1 is equal to mass in times enthalpy in. Now again, when I start off this problem, it's a complete vacuum inside of that tank, so there is no internal energy at 1. There's nothing inside of it to be internal energy there, so this is going to go away. This is going to go to 0, and I'm left with this equation. It goes like this. The internal energy, the internal energy of 2 is equal to the mass in times the enthalpy in. Okay, so now what we have is we have these two equations. We have these two equations. This is my equation, and this is my equation. So I've taken the mass continuity equation, integrated it, and simplified it. I've taken the energy equation, I've integrated it and simplified it, or I've simplified it and integrated it, however you want to look at it. And now the next step is to combine these two equations. So I want to take these two equations and I want to put them together. And I see a very easy way to do that here. Mass in is equal to mass 2, so I can write this as U2 is equal to mass 2 times H in. Now, expanding that even further, I can say that mass 2 times U2, meaning specific internal energy, is equal to mass 2 times H in. And so we have a very unique problem here where our masses are going to cancel. And so for this situation to occur, we have to say that the internal energy 2 is going to be equal to the same as the enthalpy coming in. Okay, so I want you to think about how would you solve this problem if it was a variable specific heat problem. Well, if it was a variable specific heat problem, you have enough information to set the enthalpy coming in. You could set that state. You know exactly what it is. And then once you set the state of the enthalpy coming in, you're going to go to back to your ideal gas tables for air, and you're going to try to find out when you have a U2 value, internal energy value that is equal to that enthalpy value. And then you're going to read off on the chart what temperature that corresponds to. Okay, what temperature that corresponds to. And if you want to do this, and I would encourage you to do this, what value you're going to get is you're going to get a temperature that's equal to 416.43 Kelvin. This is if you do variable specific heat. Or if you use the tables, which means using the tables. Okay. Now, we're not asked to do that. We have to do something that is constant specific heat. And that's going to take us down a little bit of an interesting path. That why I use this as an example problem, because it's not something that I would typically see that you would do. Because remember, when we do constant specific heats, we want to see something like U2 minus U1 or H2 minus H1. And we don't see that right here. We don't see U2 minus U1 or H2 minus H1. We don't see a delta U or delta H. We see a U and an H. But now we have to make a jump here. We have to say, okay, I don't have that, but you know what I could do? I could take this enthalpy, and I know enthalpy is equal to internal energy plus PV. Okay, I know that that's true. Pn, Vn. I know that's the case. And now I have two U's in my equation. Okay, we never want to break up enthalpy. I shouldn't say we never. We rarely want to break out enthalpy. But in this case, in this problem, we're going to actually want to do that. And so now what we can do is say this. Well, PV for an ideal gas, PV is equal to RT. And so I'm going to rewrite this equation as this. U2 minus Un is equal to RTN. RTN. And now with my U2 minus U1, now I can use a constant specific heat method. So I can replace this as C sub V. My computer's getting ready to act up on me. I can see that C sub V times T2 minus Tn is equal to R times Tn. Okay? Now, I don't know my C sub V. I was given the value for K. The value for K. And so remember how I find C sub V with K. C sub V is equal to R all over K minus 1 times T2 minus Tn is equal to R Tn. Okay? Now, I'm going to need to solve this, and so there's some algebra steps here. T2 minus T1, Tn, sorry, times R is going to be equal to R times Tn times K minus 1. Okay, I notice I have an R in both sides of my equation, so I can cancel this R, and I can cancel this R. I don't have to worry about them anymore. Okay, I could have done that in the first step, but I just didn't see it right away. Okay, next thing I can do, well, I can multiply through and say I have here T2 minus Tn is equal to K times Tn minus Tn. Okay. And now I see that this Tn here and this Tn here will cancel if I add Tn to both sides. And I'm left with that T2 is equal to K times my temperature in. All of that work got us down to this very simple equation that T2 is equal to K times the Tn. Okay, so what was my K value? My K value was 1.4. What was my temperature in? It was 25 degrees Celsius, but I have to add 273 per Kelvin because I'm dealing with the equation. Remember, this came from the ideal gas equation. I have to deal with things in absolute temperatures. And that gives me 417.41 Kelvin. Okay, 417.41. So 417.41 divided by minus 273. We're saying the temperature in that tank is going to be 144 degrees Celsius, which is surprising that it's that hot when that air is rushing in there. But that's the temperature that it would get to. Okay. Now remember, if the value that we got when we were not using tables was closer to was 416. Okay, that's good. It's close enough. We can go with it. That's going to be our answer. Okay, that's our answer. Now that's for the final temperature. Let's now ask the question about how much air comes in, how much air flows into this. And remember, the mass coming in is going to be equal to the mass at state 2. And we can find that by just using PV is equal to Okay, so the mass 2 is equal to PV over RT. Okay, what was my pressure? This is all at state 2. What was my pressure at state 2? Well, it was 1 bar, 10 to the 5th. Let's do 10 squared. 10 squared kilonewtons per meter squared. My volume there is 10 liters. My R value is going to be 8.314 divided by 28.97 kilojoules per kilogram Kelvin. And my temperature was 417.41 Kelvin. I want you to give me the mass in grams. That's going to be how you're going to get out of this section. Give me the mass in grams. Remember here, we're going to check our units, make sure our units work out, because right now the units don't work out in that above that mass equation. You're going to have to convert some things, check your units, but give me the mass in grams for your answer, and that will get you out of this problem, and we'll go to our second problem in just a moment.